Hi everyone, I am Sujani, Faculty in Physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss one important topic in semiconductors, that is Kronig Penny model. This Kronig Penny model is very important because it forms the basis for band theory of solids, which helps in the classification of materials. So, in this lecture, we are going to discuss about the Kronig Penny model. We have already discussed the free electron theory and the Bloch theorem in our previous videos. And today we'll be focusing on the Kronig Penny model. So, what is this Kronig Penny model? They are two scientists, Kronig and Penny, which helped us to understand the periodicity, especially of the movement of electrons in a crystal lattice. So, to understand this, we need to recollect the Blotch theorem. So, Blotch gave us a function which describes the periodicity. So, we'll have to recollect the Blotch theorem, and then we will apply the Blotch function to the periodic potential, then understand the square wells and solve the Schrdinger wave equation, plot graph using the solutions. Whatever solutions we get from the solving the Schrdinger equation, we will try to plot graphs and we will obtain the conclusions from the graph. Now, in free electron theory, what we have seen here is in quantum free electron theory, the electron is experiencing a constant or zero potential inside the metal. So, this was the basic assumption that was made in quantum free electron theory, but later on it proved to be wrong. Because this theory could explain the electrical conductivity, specific heat, thermionic emission and paramagnetism, but it failed to explain the major classification, that is the classification of materials into conductors, semiconductors and insulators. It could also not explain the Hall coefficient, which we'll be discussing at the end of this module, and also the lower conductivity of divalent metals, those metals which are having divalency, whose valence is 2. Why they exhibit lower conductivity, that also could not be explained with the help of this quantum theory. Now, to overcome these problems, the periodic potential due to the positive ions in a metal is considered. So, this also we have discussed in detail before the Blotch function. So, what we are trying to say here is the electron is not moving in a constant potential. If I take this as the crystal lattice, if you have an electron that is detached, all electrons that are detached from the atoms, you will be left with positive ion cores which are arranged in a periodic fashion, and this electron is now moving in this lattice which consists of positive ion cores. Okay, so now the potential has to be periodic. So how it is periodic, we are going to understand. Now, if you consider an electron here, okay, so the potential of the electron at the positive ion site is 0 and is maximum between 2 ions. I will consider this electron, okay, which is moving along a straight line. It is moving like this. Now, when it is at the positive ion site, this is a positive ion site. These are positive ion sites which are representing the ions, and this is the electron. There are many free electrons. We are talking about one free electron and we are trying to trace its path. How is it moving and how is its potential varying inside the crystal lattice? That is what we are trying to understand. Now, when this electron is very near to the positive ion, what is happening because of the interaction between this negatively charged electron and the positive ion, the potential is minimum. So, what we understand is at the positive ion site, it is 0 or minimum. and in between two positive ions it is maximum. Means by the time this electron comes from here to here, very near to this site, it becomes maximum. Now again at this position it becomes minimum, again here it becomes minimum and minimum. So at all positive ion sites the potential is minimum, and in between two positive ion sites it is maximum. So if I represent it along this line for clear understanding, I have shown this is along the x-axis I have shown. So these are the positive ions, and the distance between ions is also fixed. They are periodic, we said, means the distance between any two ions is the same. And if you are considering an electron which is coming near to this ion, so at this site, at this positive ion site, you see the energy is minimum. The potential is minimum here. Now in between these two sites, so the potential becomes maximum. And again, when it comes to this ion site, it becomes minimum, and then it becomes maximum. This is in between two positive sites. So this is what we are trying to understand. So we are giving away with the concept of constant potential and now talking about varying potential. So the potential that is experienced by an electron when it passes along the line through the positive ions is shown here. Means this electron is going through a sea of positive ions. We are considering it moving along a straight line and trying to understand how the potential varies. So when you see at positive ion sites, we are seeing that it is minimum. Why it is minimum? Because of the interaction of the electron with the positive ion core, the potential is becoming minimum. But when it is far or in between two ions, it is maximum. So what we are seeing here is periodicity. It is minimum, maximum, minimum, maximum, and so on. This is how the potential varies inside a crystal. Now, if you have to solve the Schrodinger equation for this varying potentials, when you are considering the potentials like this, if you have to solve it, no, it is difficult to apply the boundary conditions and put the limits to this. So, these two scientists, Kronig and Penny, what they did is they just approximated these potentials into rectangular steps. They did a small modification. What they did is, instead of considering them as smooth curves, they said they are like this. They are like potential wells, square wells, or rectangular we see here. So that is what we are trying to see here. If you see, now no more, of course, if you are having an positive ion here, the potential is minimum. Positive ion, potential is minimum, minimum. So, and in between two positive ions, the potential is maximum. Okay. So, whatever that was represented here, Kronig and Penny, they have modified it in rectangular steps because it becomes easy for us to solve the Schrodinger equation with this type of model. So, they have assumed it to be in rectangular steps. Now, if you see this figure, so what you are trying to understand here is, this is a positive ion site where the potential is minimum, and this is maximum. Now, I can say that these are wells. Wells means if I consider an electron inside this well, it has minimum chances of escaping out, because when we have assumed the electron is trapped inside a metal where at the surface the potential is maximum or infinite potential. So it cannot come out. Okay. So now I will put two regions here. This is region 1, which is the well, where the potential is considered to be 0 inside the well. Okay. And then they are separated by barriers. I call them as barrier. If I am calling this as a well, these are potential wells. So all these are barriers. They are barriers. And what is the potential at the barrier, or I can say the height of the potential barrier is denoted by V0. And I denote it as region 2. So region 1 is a well where the potential is 0. Region 2 is a barrier where the potential is V0, the maximum. So this is minimum and this is maximum. So what we have studied here is the potential is not constant, it is periodic and it varies between minimum and maximum. So we are trying to explain or put it in this form. The potential is minimum inside the well and at the barrier, wherever there are barriers, the potential is maximum. So we are denoting it in terms of wells and barriers and they are periodic. How we are saying it is periodic? If this is 0, I take this position as 0. This is the lattice parameter. So if you have an atom here or ion here, positive ion, I may have another one here. So 0 and A. Okay. So this is the width of the well. I will consider the width of the well here as A. Now they are separated by barriers of width B. So because I'm taking it on the other side, I'm putting it as minus B. So this is 0. This position will be A. This will be minus B because it is on the left hand side. So what I have plotted here is with the distance, how the potential varies. So this figure is very important for us to understand the Kronig Penny model. So whatever periodic potential we have seen here, okay, that it is becoming minimum at the positive ion sites and maximum in between, we are representing it in the form of a potential well with barriers in between. Now the Kronig Penny model is a simplified model for an electron in one-dimensional periodic potential. So how it simplifies our understanding of this periodicity and how we can apply this periodicity and solve the Schrdinger wave equation. That is why we use the Kronig Penny model. So the possible states that the electron can occupy are determined by the Schrdinger wave equation. So we have seen the Schrdinger wave equation. Once you solve this Schrdinger wave equation, the solution gives us the wave function. Once you get the wave function, you can find the probability by normalizing it. Psi square is equal to 1. And once you get this, you can also find the energy of the states, which we call them as the eigenstates. So what does the Schrdinger equation represent? Dou square psi by dou x square plus 2m into E minus V by h cross square into psi is equal to 0. So as I told you, psi is the wave function. Psi represents the wave function because we are talking about the electron which is moving. It exhibits wave nature and to represent it we are using psi. And why we are considering only x? We are considering only in one dimension. We are talking about one dimension even though crystalline solids are three-dimensional. To explain this concept, we are limiting ourselves to one dimension. So I am only talking about the x direction. Otherwise, we would have written dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square if you consider it in three dimension. But here we are limiting only to one dimension. So we are writing dou square psi by dou x square plus 2m into E minus V by h cross square. E here represents the energy and V represents the potential. And h cross is a constant which is h upon 2 pi. H is the Planck's constant here. We know the Planck's constant. So to understand this, because we are going to solve this equation, you need to know all the terms in the Schrdinger wave equation. So this is what is about this Schrdinger wave equation. Now the energies of these electrons can be known by solving the Schrdinger wave equation. And this is a time independent equation for an electron moving along the x direction. That also you need to consider. We are considering time independent equation in case of stationary waves. For stationary waves, we always use a time independent. If they are progressive, then we use the time dependent wave equation. So we are limiting ourselves to time independent wave equation. So this is the wave equation. Now we are going to explain this and also explain the periodicity. So since Kronig Penny model exhibits translational symmetry, means we are talking about how it varies along a straight line, the energy eigenfunctions of this Schrdinger wave equation will simultaneously be the eigenfunctions of the translation operator. So how we are going to get the energies or the eigenfunctions using the translational operator. So what we are using here is the translation operator T. It shifts the solutions by one period. So what is the periodicity we are considering here is A. Psi of x is equal to psi of x plus A represents the periodicity which we have discussed in the Blotch function. So any function which is of the waveform psi k of x is equal to uk of x into e power ikx is an eigenfunction of the translatory operator with eigenvalue e power ika. So how you are getting the eigenvalue is from the wave function, where e power ikx represents the plane wave and ukx represents the periodicity. So when we are considering an electron in a periodic potential, so we also have to consider the wave function and put the periodicity function. So here psi k of x is equal to uk of x into e power ikx. Now in solid state physics, functions like this means which we have seen now, psi k of x is equal to uk of x into e power ikx. These are called the Blotch functions. They are in the Blotch form because he has introduced this periodicity and gave the wave function. So the convention for describing the electron waves in a periodic medium is to express them in terms of the eigenfunctions of the translatory operator. This we have already discussed. We are trying to express the eigenfunctions, and these eigenfunctions have well-defined frequency and form a complete set that can be used to describe any wave. So whenever you have the wave functions, you can describe its wave nature very easily. And now a virtue of this model is that it is possible to analytically determine the energy, eigenvalues and the eigenfunctions. So if you are using this model, you can very well find the wave function psi of x, and you can also find the energy E of psi can be determined. And it is also possible for analytical representations or expressions for the relations of E versus K. E is the energy versus the wave vector. So with the variation in wave, how does the energy vary? Okay. So this concept of E versus K and the electron density of states could be very well explained with the Kronig Penny model. So at the end, what we are trying to see is how the eigenfunctions or eigenenergy values or the states vary with the wave vector. Now an eigenfunction is specified by K that appears in the function of in the expression for eigenvalue. Now how does it turn out to be? It turns to be the physical interpretation of K and is nearly the same as the wave number. Now whenever we are talking about a wave number in harmonic waves, we talk in terms of K. So this turns out to be the same. So this has got a physical interpretation using K. Now the energies and wave functions of the electrons that are associated with this model are obtained by solving the time-independent one-dimensional Schrdinger wave equation on applying the conditions of varying potential. So now we are going to take this time-independent Schrdinger wave equation. So this is the Schrdinger wave equation. This is time-independent. Okay. And then what we are going to do, we are applying the conditions of varying potential. So what are the varying potentials here? These are the varying potentials. So at the positive ion sites, the potential is minimum. and between two positive ion sides it is maximum, it is V naught. So we are taking this and we are applying these conditions of varying potential. Now Schrodinger wave equations for regions 1 and 2. Okay, so what is region 1? So this is region 1, which we call it as the well, where the potential is 0. And this we call as the barrier, is region 2, where the potential is maximum, V naught. V naught is maximum. Okay, so the regions are 1 and 2, well and barrier. So how do we write these conditions, put these conditions into the Schrodinger wave equation? So since V is equal to 0 in region 1, so in the original expression dou square psi by dou x square plus 2m into E minus V by h cross square psi is equal to 0. Here we will put the value of V to be 0 for region 1. In region 1, because we have considered in region 1 V is equal to 0. So this term goes to 0. So if this term goes to 0, what we are left with is dou square psi by dou x square plus 2m into E by h cross square psi is equal to 0. So in this region, that is region 1, in region 1 V is equal to 0. So what will be the values of x here? X lies between 0 and a in region 1. So we are putting the condition here for x lying between 0 and a, V is equal to 0. So when we put V is equal to 0 in this equation, we get dou square psi by dou x square plus 2m E by h cross square psi is equal to 0. This is for region 1. Now how do we put it for region 2? So in region 2 what we have? It is maximum. V is equal to V naught. So in place of V here, in place of V, we are going to put, in place of E, we are going to put V naught. So because V is equal to V naught in region 2. In region 2. So in region 2, you put V is equal to V naught. So how was the equation modified? Dou square psi by dou x square plus 2m into E minus V naught by h cross square psi is equal to 0. So what is the position if you see with respect to the position? So x lies between minus V and 0. So in this region, the value of V is maximum, that is V naught. In this region, the value of V is minimum, that is 0. So we have put both the conditions and we have got the expressions for region 1, that is equation 2, and for region 2, that is equation 3. Now these equations can now be modified because we are having too many constants. We can simplify and write the equations by substituting alpha square is equal to 2me by h cross square, because in the first equation we had dou square psi by dou x square plus 2me by h cross square psi is equal to 0 in region 1. No, this is for the region 1 when we have put V is equal to 0. So for all this 2me by h square, I will put alpha square. So let alpha square be equal to 2me by h cross square. So how does the equation modify then? Dou square psi by dou x square plus alpha square psi is equal to 0. This will be our modified equation 4. This is for region 1. Now in the second one, what we had E minus V naught. Okay. So now what we are going to substitute here is, if I write the expression for region 2. So in region 2, we had dou square psi by dou x square plus 2m into E minus V naught by h cross square into psi is equal to 0. Here what we are going to substitute is beta square is equal to 2m into V naught minus E. Why we are writing V naught minus E here is because we have considered V naught to be maximum. So we will always write, instead of taking E minus V naught, we have taken V naught minus E. So if beta square is equal to 2m into V naught minus E by h square, so 2m into E minus V naught by h square will be minus beta square. So for all this, I will have to substitute minus beta square. So there is a difference of 1 minus here. So for this, I'll be substituting minus beta square. So how does the equation modify? Dou square psi by dou x square minus beta square psi is equal to 0. Why? Because we have taken beta square is equal to 2m into V naught E by h cross square. And so this will be the equation for region 2. So we have taken the Schrodinger wave equations. We have put the conditions for the well V is equal to 0, and for the barrier, or we have taken V is equal to V naught, and after putting the conditions, we have written them in a simplified form by substituting the constants alpha square and beta square. Now we are going to see the expected solutions. So since the expected solutions of these equations are similar to the Blotch functions, it is required that psi and dou psi by dou x should be continuous throughout the crystal. When we are talking about psi represents the wave function, so its first derivative also should be continuous, and then we will be writing the general solutions. Of course, from here, you may not need the derivations for in your curriculum, but I am telling you, for those who are interested in understanding how we are getting the final expression, I am just putting some equations which you may understand, or you may leave them because in case you have to write, you are not expected to write them. So what are the solutions of these equations? Psi 1 of x is equal to a e power I alpha x plus b e power I minus I alpha x. This is for the region 1. And for the region 2, we are writing the equations where a, b, c and d are constants in the regions 1 and 2. So we have got the two equations for the two regions, and we have also got the wave functions, which are the solutions of these two equations. And now we will apply the boundary conditions. Apply the boundary conditions and also take dou psi by dou x, the first derivative, also equated to 0. What you get here is cos k of a plus b is equal to beta square minus alpha square by 2 alpha beta sin alpha a sin h beta b plus cos alpha a cos h beta b. Okay, what are the values of beta square and alpha square we have taken? We have mentioned here. Alpha square is 2me by h cross square and beta square is 2m into v naught minus e by h cross square. These are the values of the constants we have taken. Now, what are the assumptions that were made by Kronig and Penny? Okay, so slowly it is applying to rectangular well as well as square well. So the potential energy PE we are writing, or we simply say it as potential, is equal to 0 at the lattice sites, and the potential energy is equal to V naught in between the lattice sites. Between any two ions, it is maximum, we are considering it to be V naught, and at the lattice sites, that is at the positive ion sites, we have taken it as 0. This is the first assumption by Kronig and Penny. Now, as the height of the barrier V naught becomes infinity, because we said the barrier height is V naught, which is maximum, and if this value of V naught keeps on increasing and it becomes infinite, means the width of the barrier decreases. Means as the height increases, we say the width of the barrier decreases, because V naught into B is a constant. So using this assumption, whenever B tends to 0, means we are considering the potential height to be infinite. So we have sin h of beta b is equal to beta b. We will simply write for this, we will write beta b. And for cos h beta b, we will write 1. You all know about the cos functions, how we take them. Okay, so we will be substituting them, and now coming to the expression. So cos ka will be now equal to beta square minus alpha square by 2 alpha beta b into sin alpha a plus cos alpha a, after putting the conditions. And then what is beta square minus alpha square? Beta square is 2m into v naught minus e by h cross square, and alpha square is 2m into e by h cross square. So if you simply expand this, what do we get? What are the things that are common here? 2m, 2m and h cross square. So if I take 2m upon h cross square common, in the first term we have v naught minus e, and in the second term again we have minus e. So we have 2m by h cross square into v naught minus 2e. And now, since v naught is much greater than e, now we said we are taking v naught minus e because v naught is maximum, and now we have also put the condition in case v naught tends to infinity, very high. Okay, then we can simply write beta square minus alpha square is equal to 2m v naught by h cross square. We will simply neglect this value of e because e is much lesser than v naught. So what we are going to write is beta square minus alpha square. It has to be actually 2m by h naught square into v naught minus 2e. But because this value is very less, we are simply neglecting. We will try to neglect this because this is much smaller than v naught. So we are left only with 2m into v naught by h square. So how do you write this expression now? Cos ka is equal to, in place of beta square minus alpha square by 2 alpha beta, we will put 2m v naught by h cross square. So 2m v naught by h cross square, in the denominator we have 2 alpha beta into beta b sin alpha a plus cos alpha a. This becomes equation 9. So the same thing after substituting. Now cos ka can also be, you can further simplify it. 2 will get cancelled here. And if we are writing m, multiply and divide with a. So I am going to multiply this with a and divide this with a. So what I have here is ma, 2 and 2 got cancelled. So we have ma by h cross square into v naught b. Okay. Into sin alpha a, beta also will get cancelled here. Beta is also cancelled. So what we are left with is m v naught a b by h cross square into alpha a in the denominator. So we are writing it as ma by h cross square v naught by into sin alpha a by alpha a plus cos alpha a. Now we are going to substitute a constant for this because m, the mass of the electron, is constant. A is the lattice parameter which is constant. H cross is h upon 2 pi. V naught is the maximum potential we are taking, and B is also the width of the barrier we have taken. So what we are going to do now is put a constant. So we are writing it as cos ka is equal to P sin alpha a by alpha a plus cos alpha a, where P is equal to m into V naught AB by H cross square. This is very important. We will call it as the scattering power. P here is called as a scattering power. So what we have done for all these constants, we have put P. So P sin alpha a by alpha a plus cos alpha a is equal to cos ka. Actually, if you see in your curriculum, it is okay even if you are not writing all the steps. After substituting the conditions in the Schrodinger wave equation, you will be arriving this, and we will be majorly focusing on this equation. How do we plot graph and how do we analyze the graph and obtain the results? So what does this equation show? So this shows the relationship between alpha and the wave vector k. So because on the left hand side we had k cos ka is equal to P sin alpha a by alpha a plus cos alpha a. So it is giving us a relationship between alpha and k. And in the left hand side of the equation, because you have cos ka, so cos can take the values between +1 and -1 only. You know the cosine functions. So what is happening here is the left hand side of the equation can only range from -1 to 1. So there are limits on the values of alpha. So because it is an equation, we are writing cos ka is equal to P sin alpha a by alpha a plus cos a. If you are having this left hand side to be limited between +1 and -1, so this applies to the right hand side also. Means we are applying this limitations to alpha also. The values of the values of alpha here. So the system will not have those energies. Suppose if it is having values between +1 and -1, alpha also can have only those values related to +1 and -1, and only those energies, if you are talking in terms of eigenstates, only those energies are allowed. Some energies are not allowed. So wherever the energies are not allowed, there is a gap, which we call it as band gap. So they are called as band gaps, and which can be shown to exist in any shape of a periodic potential. Whenever we are talking on a periodic potential, in a periodic potential, now what we are trying to understand, because of this condition, there may be certain regions where the energies are allowed, and there are certain regions where there are no energies or energies are not allowed. Means you cannot find the electrons in such regions. So they are now separated as bands. Okay, and in the energies you will have allowed bands and also gaps, which we will call them as forbidden bands. Now let us look and understand this very clearly. We will have this equation cos Ka is equal to P sin alpha A by alpha A plus cos alpha A. How we are going to plot is along the x-axis, this is the x-axis, we have taken the values of alpha A. And along the y-axis we have taken, this is the y-axis, we have taken P sin alpha A by alpha A plus cos alpha A. This is the right hand side. This is the right hand side we have taken along the y-axis and plotting it against alpha A. Now we will consider the value of P to be 3 pi by 2. Now if you are substituting the values for every value of alpha, how the value, this value varies. So you take, say, alpha is equal to pi. Okay. So it varies between, you keep on varying the values. This is pi, this is 2 pi, 3 pi. So on the other side, minus pi, minus 2 pi, and minus 3 pi. And substitute and get the values along the y-axis. You will get a graph like this. Actually, when we see this will be called as the first Brillouin zone. Okay. Which is not included here. This is the maxima. So then you will have the curve like this. When we are plotting for P sin alpha A by alpha A plus cos alpha A versus alpha A, you get the values. When you get the values and you plot the curve, so you will get a curve like this. And on the negative side, when you join all the points, so this is how you are plotting for x versus y. Now what we need to understand here is, because there is a limitation for cos Ka. Cos Ka can take the values only between +1 and -1. So for +1 and -1, I have drawn a line. This is for +1 and this is for -1. So because there is a limitation, now these regions between +1 and -1 only are allowed. This is allowed between +1 and -1. So this is not allowed. This region is not allowed. If this is allowed, again this is not allowed. Are you able to understand? By putting the limitations, what we are getting? These shaded regions, which are allowed bands, which lie between +1 and -1. And for this curve here, this region between +1 and -1, this is allowed. And this is also allowed. So what we are getting here is, there are allowed bands separated by gaps or forbidden gaps. So what we are trying to understand, first we have started with the constant potential. We have understood that the constant potential is an oversimplified assumption, but it should be periodic. Periodic means it is moving in a potential where it varies in a periodic fashion. And after that, when Kronig and Penny have applied this model and come up with this result, now then what this equation tells us is, with the help of the limitations we have for the values of cos Ka, so we are trying to understand that only certain regions are allowed. Means in this region when there is a particle, so it is allowed and here it is not allowed. So we are separating them as allowed bands and forbidden bands. There are certain values of alpha for which you cannot have those energies. So they are forbidden. So allowed and forbidden. Now, what to understand from this graph? Cos Ka can have values only between +1 and -1, which are indicated by the two parallel lines. We are trying to understand the graph. This means only certain values of alpha. That means those values of E related to this alpha are only allowed. Other values are not allowed. And for specific values of energy, we have only one value of cos Ka. So if you are trying to find the value of E, it will have only one value for Ka. And since cos Ka is an even periodic function, you are getting the same value, whether Ka is positive or negative, that we have seen in the plot. And now, you can even further extend it to +2 pi or 2n pi also, whatever may be the values of n. Means the energy of an electron is a periodic function of K. Now what we are trying to understand here is E versus K. So now E, that is the energy or the eigenvalue, is a periodic function of K with a period of 2 pi by A. Now the allowed bands are regions where the electrons can stay. Now, if I am talking about allowed bands, means the electrons can be present in those regions, and the gaps are regions where the electrons are not present. Why the electrons are not present? Because they are not allowed. Why they are not allowed? Because we have put the limitations. Only those regions lying between +1 and -1, they are allowed. And other regions we are calling as gaps, they are called as band energy gaps. Now, what is happening to the electron? The motion of the electron in a periodic potential is characterized by bands of allowed energy separated by forbidden bands. Now, there is a restriction on the movement of the electron. There are certain regions where the electron can move, and there are certain bands where it is forbidden. It cannot go. So, this is how we are trying to come into the band theory. So, there are regions or bands allowed energy, and they are separated by forbidden bands. Now, what are the conclusions that we draw from this graph? The energy spectrum consists of alternate regions of allowed and vacant bands. So, if you see these shaded regions, they are all allowed. These are allowed. And these regions are forbidden. So, where it is not shaded, they are forbidden. So, they are alternate, no? Allowed, forbidden, allowed, forbidden, allowed, forbidden. So, that is what we are talking about, alternate region. So, whenever you see the energy spectrum, in the energy spectrum, what you see, there are some allowed bands and there are forbidden bands, and they are alternating each other. What does the forbidden band imply? So, it implies that the energy levels that lie in that region are not occupied by electrons. Means you cannot find the electrons in such regions or in such forbidden bands. So, the energy levels that lie in that region are not occupied by electrons, or you cannot find the electrons in the same. So, the allowed bands are narrowest for lower energy values and become broader as the energy increases. If you see here, these are the lower values of energy. So, here if you see, this is the width of the allowed band. Here, as you go away, or as the values of energy increases, what is happening? The width of the band keeps on increasing. This is the allowed band. So, the allowed band are narrow for lower values of energy, and as you go increase the energy, the bands are becoming broader. And what is happened to the forbidden bands? If you see the forbidden band here, this is the width of the forbidden band, and here this is the width. So, as you see, the width of the forbidden band goes on decreasing. So, what you understand here is the width of the allowed bands increases, and the width of the forbidden band goes on decreasing. Now, with increase in alpha A, the allowed energy states for an electron increases. So, that is obvious. If you are increasing the value of alpha A, the energy values are also increasing, and thereby increasing the bandwidth of the bands. That is, the strength of the potential barrier decreases. We have seen, no, the width of the allowed bands is going on increasing, and the width of the forbidden band is going on decreasing, what it symbolizes here is the potential barrier diminishes. So what we understand here is, if P is very large, P here is this value of P. Here we have plotted a graph for the value of 3 pi by 2. So what we are trying to understand, if the value of P, that is the scattering power, what we have taken, P is equal to m v naught b upon a square. So when we have taken this value of P, the scattering power, the curve crosses +1 and -1 at a steeper value. So due to this, the allowed bands are narrow. If I'm talking about steeper, means this is steep. Okay. And if this is steep, this is not steep. Now here, when it is steep, then what is happening? The allowed band is small. But when it is not so steep, what is happening? The allowed band is increased. Are you able to understand? With the value of P, the shape of the curve varies. And with this steepness, what is happening now is the width of the band also keeps on varying. So if P is large, the curve crosses +1 and -1 at a steeper angle. And because it crosses at a steeper angle, the width of the band is less. Means what we are trying to understand, as P increases, the width of the allowed bands keeps on decreasing. So due to this, the allowed bands are narrow and the forbidden bands are broad with the increasing value. That is with the scattering power. Here we are talking about the barrier. And as P tends to infinity, the allowed band reduces to one single level. So here if you see alpha A, and if the value of P goes to infinity, we will no more have it as a curve, but it will reduce to a single line. Means there is no band, it is simply a line. Means what? We are back to the case of discrete spectrum existing in isolated atoms. As the value of P increases and becomes infinity, everything is reducing to what? As what we have seen as a discrete spectrum. Now discrete means fixed values which are not continuous. So if you are putting this condition of P is equal to infinity, we will have sin alpha should have the value 0. So when will sin alpha A be 0? Only when alpha A is taking the values of ± n pi. So let us put the condition, if alpha A is equal to n pi, squaring it, alpha square A square will be equal to n square pi square. So I can write the value of alpha square as n square pi square upon A square. And what is the constant we have mentioned for alpha square? Alpha square is equal to 2me by h cross square. So we are going to equate these two. Alpha square is equal to n square pi square by A square. And the constant we have taken for alpha square as 2me by h cross square. So n square pi square by A square is equal to 2me by h cross square. So you can get the value of E from here by taking h cross square onto the other side and getting 2m down. So from here, what we get is, from this equation, what does this imply is, you get E is equal to n square pi square into h cross square by 2m into A square. So that is what we are writing. N square h cross square pi square upon 2m A square, or if you are substituting for h cross, h by 2 pi. H cross is h by 2 pi. So h cross square will be h square upon 4 pi square. So if we are writing 4 pi square and pi square will get cancelled. So you have 4 into 2, 8 m A square. So the energy value or the eigenvalues are given by n square h square by 8 m A square. So the energy levels in this case are discrete. So when P tends to infinity, what we are seeing here is the band reduces to a single line, and we are coming back to our discrete spectrum, and where the energy values are discrete. And the result is what it is similar to the energy levels of a particle in a constant potential box, where we have derived this expression E square is equal to n square h square by 8m A square or L square. It depends upon the dimensions of the box. Okay. So the same thing we are having, what energy values the particle can have. Now when P tends to 0, it is a case of a free particle. So when the value of P is equal to 0, it is a free particle. So no, that is no, means no energy barrier, means no energy levels exist are allowed. Now then what happens? You will have something continuous. So when P tends to infinity, you will have a continuous wave. So how do we get the values now? We will, because P is equal to 0, in this equation, P sine alpha A by alpha A plus cos alpha A is equal to cos Ka. We have put P is equal to 0. So the whole term becomes 0. So cos alpha A is equal to cos Ka. So if cos alpha A is equal to cos Ka, then alpha should be equal to K. Cos A and A. So therefore alpha should be equal to K, or alpha square should be equal to K square. K square is equal to alpha square. What is the value of alpha square? 2me by h cross square. Now what we are trying to write is establish a relationship between E and K. E is the energy or the eigenvalues and K is the wave vector. So with the wave vector, how the values of energy are varying. So E is equal to h cross square by 2m into K square. So from here we are writing. Okay. So just substitute for h cross h by 2 pi, and for K, the wave vector is given by 2 pi by lambda, where lambda is the wavelength. So K is equal to 2 pi by lambda. We are substituting 2 pi by lambda whole square. So how we are going to simplify this is h square by 8 pi square m into 4 pi square by lambda square. 2 pi by lambda whole square, we are writing it as 4 pi square by lambda square. This will be the value of E. So pi square will get cancelled. 4 will go 2 times. So we are left with E is equal to h square by 2m into 1 upon lambda square. So now we have the de Broglie relation. P is equal to h by lambda. So h square by lambda square can be written as P square is equal to h square by lambda square. So I can write it as E is equal to P square by 2m, or because P is equal to mv, we can also write in terms of half mv square. So the eigenvalues or the energies are given by half mv square. So if you want to refer to the equations or know more about the derivations, you can refer to these books by Palaniswamy and Engineering Physics by Gaur and Gupta, and also Dr. K. Vijay Kumar and Chandralingam, Modern Engineering Physics. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.